Welcome to the Explainer. So let's just dive right into this because today we are basically pulling off the ultimate academic heist. Imagine you're assembling this elite team of cognitive specialists just to crack the vault of the Cambridge Physics 9702 exam. The target? Every single available mark. And the security system we have to bypass? The notoriously tricky topic of scalars, vectors, adding and subtracting coplanar vectors, and of course perpendicular components. To pull this off, we really need to look at who usually triggers the alarms. We've got two suspects from past exam papers. First up is Alex. Now, Alex completely overloads every answer with just raw physics facts. If you ask Alex about a vector, you're going to get a beautiful textbook definition, but absolutely zero analytical depth. Then there's Sam. Sam rushes. Sam looks at a vector addition problem and completely misses the command words, like calculating when they should be determining and just totally ignoring the context. Both of these approaches, they leave absolutely crucial marks just sitting on the table. So, in this explainer, we're going to act as your ultimate strategist. We're decoding the exact Cambridge assessment objectives to transform those flawed red ink dancers into solid green check marks. We're going to look at the core differences between scalars, which only have magnitude, like mass or speed, and vectors, which pack both magnitude and direction, like force or velocity. But more importantly, we're looking at exactly how examiners want you to actually manipulate them.
Now, I want you to really consider the sheer weight of this statement. This is a direct insight straight from a Cambridge senior examiner. The difference between a B and an A star in physics often comes down to how well you understand scalars and vectors. I mean, why is that? It's because vectors are literally the foundational language of mechanics. If you can't accurately resolve a force into its perpendicular components, or if you kind of fumble the subtraction of coplanar vectors, well, your entire framework for kinematics, dynamics, and equilibrium just totally collapses. You end up losing those early method marks, and then that error just carries forward, absolutely devastating your final score. So the stakes are incredibly high here. But once you master the specific examiner blueprint, you hold the keys to unlocking those top-tier grades for sure.
All right, so here is our 4-step master plan for exam success today. Number 1, core principles. Number 2, technical methodology. 3, critical analysis. And 4, top examiner warnings. Let's get into it.
Starting off with Section 1, core principles.
Okay, so before you can even think about manipulating coplanar vectors, you really need to understand the rules of the game Cambridge is playing. The syllabus makes it super clear that top-performing candidates don't just memorize equations, right? They show this deeply connected, conceptual understanding that they can transfer to totally unfamiliar contexts. And this brings us to a huge dividing line, superficial breadth versus analytical depth. Let's look at our students, Alex and Sam again. When asked to determine the resultant of two coplanar vectors, Alex gives us superficial breadth. It's a generic definition of a vector and this rough, unskilled sketch. It's totally a scattergun approach. Sam, on the other hand, gives us a really rushed calculation without even stating the formula or the direction. But the top students, they use structured reasoning. We like to call it the Peel framework: point, evidence, explanation, link. Let's break down exactly how you'd apply Peel to a complex vector subtraction problem. When you use this framework in physics, your point is identifying the physical principle, like stating that the forces are coplanar and not in equilibrium. Your evidence is the specific data you pull right from the question's diagram. Your explanation is the actual mathematical resolution into perpendicular components, using sine and cosine correctly based on the given angle. And finally, your link ties it all back to the specific context of the question, making sure your final vector has both a calculated magnitude and a really clearly defined direction. Honestly, this level of analytical depth is exactly what separates the truly excellent candidates from the rest of the pack.
So, the big takeaway here is this: connect the concepts. The principal examiner reports consistently flag that candidates who actually reference cross-topic connections end up scoring significantly higher marks. Scalars and vectors don't just exist in a vacuum, guys. When you're resolving coplanar vectors into perpendicular components, you aren't just doing geometry. You're actually setting up the foundation to solve for acceleration using Newton's second law. You're gearing up to calculate work done by using the component of force parallel to displacement. And A-star student doesn't just look at a page and see a triangle with arrows, they see the actual mechanical reality of the system. They connect that vector diagram directly to how the object is going to behave in that specific exam scenario.
Moving on to Section 2, technical methodology. Let's talk about the method mark strategy.
All right, this is where we secure the bag, so to speak. Cambridge physics exams are actually pretty generous in one specific way. They will award you marks for your process, even if your final numerical answer gets, slightly mangled by a silly calculator error. But to get those method marks, your process has to be absolutely flawless. Here is the exact 5-step standardized sequence you need for processing complex coplanar vector problems. Step 1. Identify key elements. Really deconstruct the question. Are you adding or subtracting? Are the vectors coplanar? What's the angle relative to the horizontal or vertical? Step 2. Apply relevant principles. This is where you choose your analytical framework. Are you going to use a scaled vector triangle drawn tip to tail? Or are you going to mathematically resolve the vectors into their perpendicular x and y components? Step 3. Execute the analysis with super clear working. If you're resolving, clearly write out force in the x direction equals force times cosine theta. Show the substitution. Show those intermediate values. Step 4. Verify your results. Basically just check for reasonableness. Like if you're subtracting a tiny vector from a massive one, does your resultant magnitude actually make logical sense? And finally, step 5. Present it in an appropriate format. We're talking magnitude with the correct significant figures, the right SI unit, and, crucially for vectors, the direction, which is usually stated as an angle relative to a specific axis.
And speaking of appropriate formats, we really need to look at the strict presentation conventions that you absolutely have to stick to. We're talking proper headings, correct terminology, appropriate formats, and crystal clear annotations. Look, if you're drawing a vector diagram to find a resultant, your scale has to be explicitly stated on the page. For example, 1 centimeter represents 10 newtons. Your lines literally must be drawn with a ruler. Your angles have to be clearly labeled and measured precisely with a protractor. Clear annotations mean identifying exactly which arrow is the resultant, which is usually marked with a double arrowhead. If your presentation is sloppy, the examiner just cannot confidently award you those vital method marks. It's as simple as that.
All right, Section 3, Critical Analysis. Let's get into evaluative thinking.
Okay, we are officially entering the high-stakes zone now. This is where we move way beyond just describing what a vector is, and we start actually evaluating complex physical scenarios. Evaluative thinking means questioning assumptions, considering different perspectives, and really justifying your decisions with solid evidence. Let's put this to the test with our first mental challenge, the data scan. Imagine a complex data table right in front of you, showing the horizontal and vertical components of an aircraft's velocity under changing wind conditions over a 60-second period. Your job is to extract the core trend. What you need to be looking for isn't just the raw numbers, but how the perpendicular wind component actually affects the resultant vector without changing the forward velocity component at all. Next up, challenge 2, find the flaw. Think back to a sample paragraph from our student Sam. Let's say Sam writes, to find the resultant force, I added the magnitudes of the two coplanar forces together because they are acting on the same object, resulting in 50 newtons. Can you spot the flaw there? Sam just treated vectors like scalars. You literally cannot just algebraically add the magnitudes of vectors unless they are acting in the exact same one-dimensional line. Because they are coplanar and acting at an angle to one another, they absolutely must be resolved into perpendicular components or added using a vector triangle. Boom, Sam just lost all their analytical marks.
So, to avoid Sam's fate, you've got to use this critical flow, deconstruct the given information, solve systematically in logical steps, and evaluate for reasonableness and justify. Which brings us to challenge 3, speed writing. If I gave you a 30-second timer right now to write one perfect Peel paragraph explaining how to determine the perpendicular components of a velocity vector on an inclined plane, what would you write? Well, your point would be that the velocity vector must be resolved into components parallel and perpendicular to the plane. Your evidence is the given angle of the incline and the initial velocity magnitude. Your explanation is that using trigonometry, the perpendicular component is calculated as v multiplied by the sine of the angle of the incline. And your link? You'd say this perpendicular component is crucial for determining the normal contact force in a dynamic context. Now that is a 100% perfect mark securing paragraph.
Finally, Section 4, Top Examiner Warnings. Let's look at the top 3 mistakes you need to avoid.
Now that we've essentially built the ultimate answering system, we need to talk about the security lasers you have to dodge. We have literally combed through the Cambridge Principal Examiner reports, specifically for the 9702 syllabus regarding scalars and vectors, just to find out exactly where this heist goes wrong for most students. Here are the top 3 reasons candidates bleed marks. First, vague answers that lack specific details. Just saying use trigonometry to find the vector is way too vague. Saying resolve the 50 Newton force into a vertical component using 50 sine 30 degrees, now that is specific. Second, forgetting to check format and presentation. This one happens all the time when subtracting coplanar vectors. Students will correctly reverse the direction of the vector being subtracted, they'll draw the diagram perfectly, but then they completely forget to measure the final angle, or they fail to state whether that angle is above or below the horizontal. Look, a vector without a stated direction is just a scalar, and you will lose the mark. Third, answers that aren't specific to the context given.
This is honestly the most dangerous trap, and it brings us right to our final, most critical alert.
Examiner alert. The absolute classic mistake here is providing generic answers that are not specific to the question context. If the exam question is about a ship being blown off course by a crosswind, your explanation of perpendicular components actually has to talk about the ship and the wind. Do not just talk about a generic force A and force B. You always have to link your physical principles directly to the scenario they give you. Your equations must reflect the actual physical reality of the problem. If you just recite some memorized method without mapping it onto the examiner's specific scenario, your analytical depth just drops to zero.
So, I'm going to leave you with this final provocative question. When you sit down to practice your next past paper, is your next answer going to be completely specific to the context, utilizing the Peel framework and our systematic methodology, or will it just be another generic guess? Use these strategies, practice them consistently, and go pull off the ultimate physics heist.